Well, this video is about error correction in the transmission of data. It's the simplest sort of error correction. It's going to be done using repetition of bits. But first let's talk about what an error might look like. Here we're trying to send a binary number, number 11 decimal in binary, and when we transmit it over whatever communication channel, whether it's over a wire using electrical impulses, or through the air using sound waves, or using radio waves, there are various sources of interference. And here I'm talking about a type of interference that could possibly wipe out a single bit. It could be a static crash over radio frequencies from a nearby thunderstorm. It could be an unexpected electrical impulse generated in a wire that's transmitting data by some electromagnetic field from another computer or any other source. It could be an unexpected audio tone if we're talking about audio. And in fact, I am interested here in transmission of, say, commands via audio. You can think of touch tone telephone tones as an example of that. In my case, it's going to be sound waves traveling through the air rather than over telephone wires. You could think about a remote control based on audio tones. That's the sort of thing I'm talking about. And I would like to have a way, instead of, if there's an error like this, instead of my binary value 11 being changed into the binary value 15, I'd like to be able to correct that error without having to repeat the transmission. And that's what forward error correction is, and that's the type of error correction I'm talking about here. And one way to do this, the simplest way probably, using repetition, is instead of sending single bits like this to repeat each bit, the simplest scheme is repeating each bit 3 times. And so we repeat the 1 here 3 times, the 0 3 times, the second one 3 times, and the last one 3 times. And then if we get a source of noise, which in ham radio jargon is called QRN, N for noise, I guess. If there's some noise that wipes out one of the zeros here and probably replaces it with a 1, if we can detect that fact in the receiver and then realize that if a majority of the bits are ones, then we should decode this as a 1. If the majority of bits are zeros, taken in groups of 3, then we should decode that as a 0, in spite of the fact that it was originally sent as all zeros, and so on. Then we can correct our received data to correspond to the data that was actually sent, the 1011, instead of the 1111 that we get up here. And so this is an example of error correction in the time domain. By that I mean that our repetition is occurring sequentially in time. We're repeating the bit 3 times as time goes by. That would be one type of error correction that we could use here. Another type would occur in the frequency domain, and that's what I'm actually interested in here, where we're repeating our command at 3 different frequencies. It could be audio frequencies, it could be radio frequencies. Okay, and the sort of interference that I'm talking about here is a little bit cleaner. It's typically coming from another source of transmission. In radio frequency world, this means another station is transmitting on this frequency F1. And most radio signals are going to be on a single frequency rather than on multiple frequencies, though of course they do have some bandwidth. And we would have to space these frequencies out enough to allow for that. But the idea here is that if some interference here does something bad to our signal on one frequency, well, for example, suppose all the bits get flipped, all the 1s to 0s and 0s to 1s, But that's going to happen, I'm going to assume, on one of the three frequencies at most at any given time. And so a single error correcting scheme is appropriate here. And we just take the majority of the three signals, which in this case is ones, and translate that as a 1 in our final result. And here, even though we have an illegitimate 1 in here, the majority of the received signals are going to be zeros, and so we'll decode that as a 0 and a 1 and a 1. Okay, and still get the correct output corresponding to our initial input of 1011 or 11 decimal. So it's implementing this frequency domain repetitive error correction of the simplest sort that I'm interested in doing. And it'll all start with figuring out how to decode something like this or this using logic gates. Well, this project gives me a chance to build some logic gates, AND gate and an OR gate, basically from scratch using transistors. I could build them using simple switches or relays, but transistors are very cheap, and these are probably the most plentiful transistors in the world. The NPN transistor, the 2N2222 transistor. And the circuit for the AND gate that I got comes from the Hyperphysics website, and just uses two 2N2222 NPN transistors, a couple resistors, and two inputs, input A and input B. Basically what's happening is that we have the transistors connected in series, like a pair of switches in series, which I have drawn out here. If you have two switches in series with a light bulb and a battery, then if you close switch A, nothing will happen because there's still an open circuit here with switch B. Same thing if you close just switch B, nothing happens. But if you close both A and B, then there's a path for the current to flow through the light bulb and back into the battery again, and so you have a illuminated light bulb. Here I'm using a LED instead of a light bulb, and you can see the two 2N2222 transistors and two push buttons. So if I push one of the push buttons, push button A, let's say, nothing happens. If I push button B, nothing happens. But if I push them both at the same time, then the LED lights up. And so that's an AND gate. We have also a schematic on Hyperphysics of OR gate, again using 2N2222 transistors, but now they're connected in parallel. So we have the emitter of one connected to the emitter of the other, and the collector of the first one connected to the collector of the second one. And that's the same as having two switches hooked up in parallel. In this case, they're just simple switches instead of transistors, but they do the same thing. If I close B, I have a complete path for electricity to flow from battery through the light bulb and back again. Same thing if I close A by itself. And if I close A and B, of course, we have two paths for the electricity to follow, and so the light will light up. And so we're going to take a look at that setup over here. The second pair of NPN transistors I have here are connected in parallel with each other, so that all I have to do is press one of the two push buttons, say push button A, and the light lights up, or push button B, or both. Everything lights, the LED lights up in that case also. So the basic circuits specified by the Hyperphysics work very nicely, and So now we're in a position to think about using and OR gates to make a circuit that will detect any majority out of 3 voters. Any pair of them voting to turn the light on should turn the light on. Anything less than that, pushing any individual switch, should not turn it on. And again, pushing all 3 should again turn on the light. So we'll have a go at that next. So then the question arises, how do we combine and OR gates to make a circuit that can detect a majority of inputs being turned on? So then to turn on a LED, for example, or a little audio oscillator or something, something to process the output. This is a symbol for an AND gate, which in our case is 2 transistors connected in series. And this is a symbol for an OR gate, which would be 2 transistors connected in parallel. And we've got a little bit of Boolean logic symbolism going on here. Signal A is ANDed together with signal B in this gate and produces the output represented as AB, which is like A times B in arithmetic. This is A and B. It's going to behave like A times B in a way that we'll see in a second here. The OR gate is ORing together the AB and BC outputs, and the plus sign is used for the output of an OR gate. It's AB, A and B, or B and C, represented symbolically here. And then finally, this OR gate is ORing together the A and B or B and C with the A and C output of this AND gate, giving us an output represented symbolically this way. Okay, and so this is sort of a natural way of thinking about how to detect a majority. We're going to detect any minimal majority, which for 3 voters, a minimal majority is A and B, or B and C, or A and C. Takes 2 of the 3 to make the minimal majority. And of course, if all 3 vote to turn on the light, then that's a majority also. But this is going to detect that because in that case, all 3 of these outputs are going to be on. And so certainly we're going to have that detected in the final output here. Since it detects any one of the 3, it'll certainly detect all 3. So the question arises of, is this the simplest circuit that will do that? And so what you need to do is think about how you could simplify this expression, which now involves 1, 2, 3 AND gates and 1, 2 OR gates. And yes, if we take this expression, rewrite it down here, and then factor it, well, we can factor it in multiple ways, but I'm just factoring it by factoring the C out here from these 2 AND statements. And yes, that's the distributive property of AND over OR, just like the distributive property of multiplication over addition in arithmetic. That's something that you can prove to yourself using truth tables. You get exactly the same truth table result from this as you do from this. Okay, and so that involves 1 less gate because we have 1, 2 OR gates, and here's an AND, C and B or A, and here's an AND. So whereas up here we had 3 AND gates and 2 OR gates, down here we get away with 2 of each. And so just whip that circuit up here. Here's our 2 AND gates, here's our 2 OR gates, and here we have A and B coming over here and being ORed together with C, which is here, and B plus A, or A plus B, of course, is the same, which I have right here. They're being ANDed together there and giving us our result. Okay, so we can toss out one of the OR gates, which is fortunate because I only have room on my current breadboards for 4 of these logic gates plus the 3 switches. So we'll take a look at that circuit in a minute. Well, here we have the final circuit, which involves an AND gate, which is right here, and an OR gate, which is right here, another AND gate, which is right here, and a final OR gate, which is right here, and then output being displayed by the LED here. So we'll see, does it do what it claims to do? Have I wired it correctly? Well, no single button, push button, should light up the LED. So A voting by itself to turn on the LED does nothing. B voting by itself to turn on the LED does nothing. C by itself does nothing. But any pair constitutes a majority, and any pair that votes to turn on the light, like A and B here, yep, that turns on the light. How about B and C? Yep, that turns on the light. How about A and C? Yep, that turns on the light. How about all of them voting to turn on the light? Push all down, yep. So, successful circuit. The final step will be to add devices to these logic gates that will detect a single audio frequency. Here's a device, it's an LM567 connected to a microphone, and with an external resistor setting, it should be able to detect frequencies just around 500 hertz. So a bandpass filter for 500 hertz, which will then, since it's by default is on, we want to use a NOT gate here to invert the output so that by default it will be off and then turn on when it detects a 500 hertz signal. And the same thing here for a 700 hertz and for an 1100 hertz. I don't know, these tones may be too close together. They certainly should not be multiples of each other, because anything, say, that produces a 500 hertz tone is also going to produce all multiples of that, like 1000 hertz and 1500 hertz, so we wouldn't want these to be set to detect those harmonics, and so on. So, and these are not harmonically related, so if that's all that's needed, then this should be fine. If they're not far enough apart in frequency for the simple audio filters on these little frequency detecting boards to work, then we'll space them out further and see if we can do it that way. But hopefully they're bandpass filters. I'm a little bit skeptical about that because they're so simple. I'm just adjusting a single resistor to set the frequency. They may be low pass filters, and so this one may be able to reject these two signals when I have it set to detect 500 hertz. But this one, if it's a low pass filter, would detect both the 700 hertz and the 500 hertz signals, and so that would not be ideal. We'll see. We've got 2 to 3 weeks, maybe a month, to wait for the parts to get here. So we'll find out then.